All right, everybody, welcome back. I hope everyone had a good weekend. So we were chatting about the snow and what everyone did on the weekend, and spring, which will eventually show up around here. Not one word from those people who are, in much more tropical climates and the like. So couple of announcements. As I mentioned in an email to everybody yesterday, Hayden McNeil website is kind of going up and down like a yo-yo. I put a monitor on it, tracker on it, and yeah, it's literally been going up and down from about 3 o'clock yesterday onwards. It was currently up when I looked earlier today, but I don't know what the status of it is right now. I had mentioned giving an extension on what was due today, but I already did that. I forgot that I had already extended the due date for the freezing point depression experiment to next Monday, because we're covering that material this week, and I decided just to be nice and generous and go from there. So that's still due next Monday, and hopefully Hayden McNeil will have figured out their website and gotten that resolved before then. The other thing that I wanted to talk about is, yes, course notes. I did update the course lecture notes, and they were put online on Friday or Saturday morning, but I didn't actually put in notes 3. I just updated notes 2. So if you haven't gone on there and downloaded the latest student instructional notes 2, please do so, because I will be going into that today. So that's kind of where we are at for information. I will have more information on your midterm on Wednesday, so I'll talk about that then. So last day we were looking at phase diagrams, and we just need to get to the right page. Had finished off discussion on phase diagrams. This is a typical phase diagram. This is actually one of the simpler phase diagrams where there is solid, liquid, and gas phase. And it tells you the conditions, the temperature and pressure at where each state is stable. Each of the lines, sublimation, vaporization, and fusion, reference an equilibrium between solid and gas for sublimation, liquid and gas for vaporization, and solid and liquid for fusion. Excuse me. And we also introduced this idea of supercritical fluid. It's another state of matter. It just doesn't happen to exist naturally under ambient conditions on Earth. We can create supercritical fluid states for CO2 and for other things reasonably easily and here, but it doesn't exist naturally on Earth. The other thing that we saw is that here there's only one state of solid CO2, but for many compounds there's more than one state of CO2, or solid, excuse me. For example, for carbon there's diamond and graphite, so you have another equilibrium line between graphite and diamond, and we don't know where the line is between diamond and metallic, but we can produce metallic carbon as well. And so this idea of a triple point, which collects 3 different states of matter, there's more triple points depending on the number of states. Probably the most studied solid we have, or compound we have, is water, and it is obvious from the blue line being discontinuous that there are different states of solid water, and this is what is known to this point in time. I believe there's up to 18 or so different states of water that are known. All right, that takes us to this. I believe we completed this in class the last day. Did anyone have any questions on any of these examples here? Any questions on these? All right, that's fine. The last thing I wanted to do in discussion of phase diagrams is this page and then one more example. We talked last day about how water, when it forms a solid, actually has a lower density. So that allows ice to float on water. I want to go back to the structure of ice, which is right there, and point out that you have, you have a nice hexagonal arrangement of the water molecules, but there are fairly large holes in solid ice. The reason why ice is more dense as a liquid is in order to form a liquid, you just need to break one hydrogen bond. So if I break this hydrogen bond right here, this hydrogen can actually slip into this open cavity of the hexagonal structure. So allowing it to slip in there allows the other water molecules to get ever so closer together. It's only about a 4% difference between solid ice and liquid water at zero, and that is due specifically because that hydrogen bond, when it breaks, it allows the other water molecules to get slightly closer together. What I had for you is the question on how does that explain soil formation, aquatic life, and tissue death during freezing. So if you want to answer any one of those in any order, type your response in the chat. How is the fact that ice is less dense than water responsible for soil formation, aquatic life, and tissue death during freezing? Go for it. Anyone got any idea? How is soil formed? The Earth, early history of Earth was that it was a rocky ball, basically a volcanic lava surface that cooled. How did we get soil? Thanks to water. Erosion, as it solidifies, as it expands. Erosion. Well, erosion is a perfect example. When you have cracks in rock, water gets in there, freezes, breaks apart the rock, and that process, happening millions of times, breaks the rock into smaller and smaller bits, and you see the weathering aspect of it, another term for it, but literally water getting in between the cracks of the rock, breaking it apart, get it smaller and smaller, and eventually grinds it down to small enough particles that organic matter, the organic matter that would be part of that originally, allowed for, growth and the regeneration surrounding those soil particles, and you end up getting, soil, those minute rock particles to give you soil. How about aquatic life? Good, Catherine, excellent response. Ice floats, and the aquatic life survives beneath the ice layer. Ice does a lot of things when it is on top of a lake or river, stream, whatever the case is. If the ice layer wasn't there, what ends up happening is the water will churn and brings the warm water to the surface because it's less dense, and it gives off its heat. So the entire body of water will cool down considerably if there isn't a layer of ice on top of it. That happens in flowing water more than it does in still water. So river water gets colder because it's harder for a layer of ice to form. Secondly, that layer of ice, once it forms, actually acts as an insulator. Okay, that plus snow on top of it prevents heat from escaping out the top of the lake, and you end up with a region underneath that is reasonably thermally stable and allows for the aquatic life, the plants, the animals that are down there, to survive. They survive close to 0 degrees Celsius, so they're in a bit of a stupor, not a hibernation for most of them. And it is, over time, becomes anoxic. It gets low on oxygen, and so that also introduces a stupor. If you don't have enough oxygen in the lake, you end up getting fish kill. That is, the oxygen gets to a point where the animals can't survive, and so come spring, a bunch of dead fish float to the surface. Not great. The last one on there is tissue death during freezing. Anyone want to take that one? Okay, so tissue death during freezing doesn't preserve tissue, but it breaks the cell wall. Two reasons. Catherine's comment was that it expands, yes, but when ice crystallizes, it actually crystallizes as very sharp as needles. It forms along a path that is not, well, needle-like. So it looks like frost, actually, would be a great example, frost on a windshield. Or when you take a package out of the freezer and you look carefully at the water that is crystallized outside or on the surface of it, it is sharp little spikes of ice. That is how it crystallizes. And so in the tissue, if the muscle is moved, if the tissue is rubbed as a result of trying to warm it up, you're literally driving those ice crystals through the cell wall, causing more damage. Historically, the idea was to rub the surface area, create a little bit of heat, and warm the area. That caused more tissue damage than just wrapping it with something that is warm, applying heat to it, causes less tissue damage. Good, thank you very much. Now, this next bit requires you to talk with some of your grandparents or parents if you're older. And if you ask them how decaf coffee tastes or used to taste, what they'll tell you, and I'm going to quote from my grandmother, it tastes like crud, end quote. The original decaffeination process was to use benzene or ethyl acetate, soak the beans in that, and the caffeine preferentially dissolved into the benzene or ethyl acetate. Benzene, by the way, is carcinogenic, but hey, they didn't know that back then. Unfortunately, benzene, ethyl acetate, and whatever else they were using ended up removing more than just caffeine, and so what was left, ground and turned into coffee, did not taste like regular coffee. So decaf coffee got a really bad reputation because of that. Subsequently, there have been a number of different processes developed. The one I want to talk about is the selective removal of caffeine by supercritical carbon dioxide. Now, there's a lot going on in this picture here, but I just want to kind of illustrate what's going on, talk it through it. So everything is done in a counterflow operation. The coffee beans move in one direction, the carbon dioxide moves in another direction. The reason for that is to extract the most caffeine, in this case, out of the beans. Most extraction processes work in counterflow operation. If you have someone who needs dialysis because of kidney failure, the dialysis solution moves in a different direction than the blood, and you get a greater removal of the toxins. What was the other one I had in the back of my head? Oh, heat exchangers. Heat exchangers in automobiles or in your home for furnaces. You have things moving in opposite direction to take the most heat out or most cold out of the flows. So here in this picture, coffee beans are moving down. Those coffee beans are just pre-soaked in, I actually don't remember what, but they're pre-soaked in something. They're moving downwards. Carbon dioxide is pumped in at the bottom and moves upwards and removes the caffeine from the coffee beans in a counterflow operation. The caffeine then comes down and goes through another counterflow operation with water. Water moves downwards, carbon dioxide moves upwards, and well, the caffeine preferentially goes into the supercritical carbon dioxide. As soon as it's not supercritical, it preferentially settles into the water. Caffeine is very soluble in water. And so then the water filled with caffeine just goes through a crystallization process, i.e. it's cooled down. Caffeine precipitates out a solution, and you get purified caffeine. And this entire process is repeated in that you have got the pump creates supercritical carbon dioxide, and the water is also pumped through this recovery scrubber. What you're left with is pure caffeine, which is a beautiful white flake crystal. One of the labs I was doing as an undergraduate myself, you had caffeine. It was like 3 kilogram container of caffeine, and it looked really cool that it had been removed from coffee beans and the like. So that's how one application of supercritical carbon dioxide, or supercritical fluids in general. Another application of supercritical fluids actually is in dry cleaning. Some of the dry cleaning processes use supercritical fluids to remove tough stains and dirt from clothing. That concludes chapter 12, and we're going to move into chapter 14 right now. So some of this material is review, like 14.1 to 14.4 is review, and I'm just going to briefly go over it. Units, changing concentration, that type of idea. Not going to do any examples on it. It's what you've been doing all the way through this course. 14.5 to 14.9 is we're going to spend today and Wednesday covering that material. So before I move into chapter 14, did anyone have any questions on this last bit in chapter 12? Give you a few 20, 30 seconds to come up with any questions before I move on. All right, sounds good. So to look at concentration, there are actually many different ways in which we can report concentration. Currently, the most common method is molarity, moles of solute per volume of solution. Historically, molality was commonly used, which is moles of solute per mass of solvent. The nice thing about molality is that it was independent of temperature. The mass of the solvent doesn't change, the moles of the solute doesn't change as a function of temperature. Molarity, as you increase the temperature, the density changes, the volume increases, and so the concentration in molarity is a function of temperature. It is not in molality. Molality was historically used. So if you're looking things up in data tables and the like, just realize that prior to 1970s, 1960s, it possibly was being reported as molality. And like a number of equilibrium constants in tabulated books are molal-based, not molarity-based. It's relatively easy to convert between the two. Well, literally all you need is the density, but it does require conversion to use them in today's molarity-based units. Mass ratio, and the next three are actually more common in, well, analytical chemistry for some, but in society. Mass ratio is mass of solute over the total mass, and we see that as mass fraction, mass percent. Out on the labels that you find on products could be M/M, mass of solute over mass of solvent, total mass, excuse me. Parts per million, parts per billion, parts per trillion are all mass-based. Volume ratio, volume of solute over the total volume, often reported as V/V. Where you'd find that is if you go into a liquor store and you buy alcohol, or you buy hydrogen peroxide in a drugstore, or you buy mouthwash, and it will tell you the concentration of alcohol, for example, as 12% V/V for wine, 40% V/V for spirits of sorts. So volume ratio is volume of solute over the total volume. And lastly is mole ratio, which is, of course, the moles of solute over the total moles. And you see mole fraction, mole percent. The other thing is that sometimes parts per million, billion, and trillion are on a mole ratio, not a mass ratio, and that may add to confusion. Commonly for gases, it's by moles rather than by mass. Sorry. I don't make the science. I'm trying to change it, but that's the way it is right now. Now, the textbook tells you that parts per million is mass-mass ratio. Yet it has the following table on whatever page. Keep in mind that 1 part per million is 1 microgram per liter, or 1 part per billion is, or 1 milligram per liter. Part per billion is 1 microgram per liter. How do you explain this discrepancy? The textbook says it's mass-mass measure, yet it talks about milligrams per liter. How do you explain that? Anyone? And I'm going to call it an error. The error that the textbook is making, as someone put it in the chat, is that it is assuming you're working in aqueous solution. In aqueous solution, yes, 1 liter of water equals 1 kilogram. But not everything is in aqueous solution. And so you need to look at a better way of presenting this information in the sense that, for example, let's consider 5 parts per million of mercury in soil. As an analytical chemist, this would be something that you could be measuring. You're getting sent a soil sample, and you want to report the percent, the amount of contaminants. Very low concentration stuff is reported. Parts per million, billion, trillion, very common. But 5 parts per million of mercury in soil, which by the way is a lot, but we'll just go with that. It is much better to present that as 5 grams of mercury over 10 to the 6th grams of soil. Okay? This allows for direct conversion to moles of mercury, to volume of soil if you know the density of soil and the like. This also works if it happened to be in water. We would have 5 grams of mercury in 10 to the 6th grams of water or solution. Okay, so this process is much more generally applicable, whereas what was presented in the textbook is limited only to aqueous solutions. So that is only true for water. It is much better to use, or always use, what I just presented here. 5 parts per million is 5 grams of solute over 10 to the 6 grams of solution. So this was already presented, but it's important, and this puts a slightly different context on it, gives you more information. We're looking at intermolecular forces and how they dictate the solubility. Ultimately, everything in science relates to energy. Everything is an energy-based process, and intermolecular forces are a measure of the energy. The important thing to consider when you're looking at solubility is the intermolecular forces that exist within the solvent and that exist within the solute. How much energy does it take to break those bonds? And then how much energy does it take to form how much energy is released forming intermolecular bonds as you dissolve the solvent and solute together? So if there is more energy forming these solvent-solute bonds, the solution bonds. If those bonds are stronger, more energy is released than was required to break it, and you end up with an exothermic process. If the bonds being formed are weaker than solute and solvent together, then you have an endothermic process because the solution bonds are weaker than separate. And If it happens to be that the bonds forming are about the same energy as the bonds being broken, so you have a reaction enthalpy or a solution enthalpy that is close to 0, then you have what is called an ideal solution. A lot of the stuff we're going to be talking about is based on ideal solution, and then we're going to see how deviation from ideal is an indicator of exothermicity or endothermicity of the process. What I just described is like dissolves like, but it's not polar dissolves polar, ion and nonpolar dissolves nonpolar. It's measuring like bonds, the strength of the intermolecular bonds in solvent and solute versus the strength of the intermolecular bonds in the solution itself. As they're similar, then like dissolves like. Same application, different context. I drew this figure for you in the past. This is just another one where you've got a solid. This is sodium chloride. Over on the left-hand side is a solid. And what ends up happening is that the individual ions, the sodium ions are stabilized by ion dipole bonds with the oxygen. The negative chlorine is stabilized by ion dipole bonds with the hydrogen, with the hydrogen atoms on water. So you're breaking apart the ion-ion interactions in sodium chloride to form a lot more ion dipole interactions in the solvent. You're also breaking apart the hydrogen bonding in water. So another question for you. Why are highly exothermic solution enthalpies common, but highly endothermic solution enthalpies less common and not as extreme? There's a lot of data on this table. I just wanted to present it, but the maximum endothermic energy is 50.5 kilojoules per mole, somewhere in here. There's not a lot of endothermic energies above 30 kilojoules per mole. The exothermicity is negative 88.9 kilojoules per mole, and there are many, or a good number, of exothermic reactions below negative 30. Why is that the case? Anyone? Anyone got a suggestion on that? Why don't we like endothermic solutions? What does that say? What does it say about the solution being formed and the bond energies for endothermic processes? So the end result is on this slide, this answer. It tells you that the solution bonds are weaker than separate. The reason why we don't see a lot of highly endothermic solution enthalpies is because the bonds being formed are weaker. If you've got strong intermolecular forces in the solvent, strong intermolecular forces in the solute, why would they break apart to form weaker bonds in the solution? They would prefer to stay as pure solvent, pure solute, and you don't get dissolution. It is energetically favorable to stay as solvent, solute, and you don't get dissolution. So things that, and that is ultimately why you don't see highly endothermic solution enthalpies. Highly exothermic, that's great, that's beneficial, because you're breaking apart weaker bonds and forming really strong bonds. That's an exothermic process. You're energetically more favorable to form these bonds, and so you see highly exothermic solution enthalpies, but not highly endothermic solution enthalpies. On this figure, just plotted the solubility as a function of temperature for a number of salts. And notice that in general, the solubility increases as a function of temperature. Just generally, it goes up as a function of temperature. All of the salts on the right-hand side all of them have at least one ion that is +1 or -1, because higher ionic charges make it harder to dissolve. So things like calcium oxide or iron oxide don't dissolve in solution because it's harder to break apart the +2, +2, +2, +3, sorry, +2, -2, +2, -3, whatever it happens to be, bonds. So you need to have one or more having a +1 or -1 charge. And that actually relates back to what's presented here. It would be a very endothermic process if you were trying to dissolve calcium oxide. It's just not energetically feasible to do that. Yes, so solid solubility increases as a function of temperature. Gas solubility decreases as a function of temperature. We saw that previously. And so while the units are different, this is mole fraction instead of percent, it's very low mole fraction of gas in water. Interestingly, xenon over here on the top is more soluble than the rest, and that is due to the polarizability of xenon. You are going to get stronger induced dipole-dipole interactions, which is what would need to form for gas to dissolve. You're going to get stronger induced dipole-dipole interactions when you have a greater polarizability. And xenon is more polarizable than things like methane, oxygen, nitrogen, etc. That's why it has a higher solubility. The bonds are stronger. So in the previous two figures, we saw that the solubility of ionic entities generally increase, whereas the solubility of gases generally decrease with temperature. How can this be explained in the context of solubility enthalpy? And how does this relate to solubilities? If we go back and look at these figures, the bonds that we're forming are actually stronger. Here the bonds are stronger. I just want to point out, just because it was brought up in the other class, that if you have a mass percent sucrose solution, it's 80% sucrose, 20% water. So 80 grams of sucrose will dissolve in 20 grams of water to give you a homogeneous solution. That's a fairly thick syrup, just pointing that out. Anyway, the reason why these generally increase with temperature is because you're able to break the weaker solvent-solute bonds more readily, and you're forming stronger ion dipole bonds. I should point out that when you take this thing up to the boiling point, the solute stays in solution, and the weaker solvent bonds, in this case it being water-hydrogen bonds, those hydrogen bonds break so that you actually boil off the solvent. You don't get rid of the solute as you increase the temperature. It just preferentially stays in solution. Here, of course, it's the weaker bonds that get broken easier. Here it's the gas bonds, the induced dipole-dipole bonds of the gas in the solution that get broken more readily, and what that does is it ends up ejecting the gas molecules from solution. You are able to remove gases by boiling the solution. And that's one common way of getting degasifying a solvent. In organic chemistry, they degas solvents. In organic chemistry, we degas solvents. If you happen to have a distiller for water in your home, if you do distillation, you have to re-aerate the water or else it tastes bad. Distilled water, pure distilled water without any dissolved oxygen in it, actually tastes quite bad. Have it, shake it up with air, and you get oxygen in there, and it tastes fresher. Now I want to start looking at the vapor pressure of solutions. When we were looking at equilibria, one of the first things we did at the beginning of the equilibria unit was look at the thermodynamic equilibrium constant. And the thermodynamic equilibrium constant retains the normal reporting state of the reagents. Pressure for gases in whatever unit, concentration for solutes, usually in moles per liter, historically moles per kilogram, molality. The dissolution of a gas in solution is an equilibrium problem. And so you simply have A in the gas phase in equilibrium with A in solution phase. The equilibrium constant would be concentration of A dissolved A over the partial pressure of A in the gas phase. And you can rearrange that to get the expression presented there. Unfortunately, we don't use that. The study of vapor pressure was not correlated or not linked to equilibria until, well, much later, and the historical methods using what's called Raoul's law and Henry's law still are applicable, and that's what we're going to be looking at now. So because of what happened historically, we don't have a single equation that explains the volatility at all concentrations. It just doesn't exist. However, there are limiting relationships for really low concentration entities, solutes, in which case Henry's law applies to solutes, and really high concentration entities, the solvents, and it's Raoult's law that applies to solvents. All of this work assumes you're working with ideal solutions, where the enthalpy of solution is close to zero. Non-ideal solutions produce deviations. From what we're going to look at. And so what we're going to look at is what an ideal solution is going to do, and then we're going to see how deviations affect that, and that is due to the non-ideal nature of solutions being formed. So Henry's law states that the solubility of a volatile solute is proportional to its partial pressure. So C is the solubility, KH is Henry's constant, and PA is the partial pressure of A. Henry's constant has a number of different ways that it's reported. Sometimes capital K, sometimes different values. If you actually really want to confuse yourself about Henry's law, look at and read the Wikipedia entry on Henry's law, because it presents at least 12 different Henry's law constants, each subtly different, some on mole, some on mass, some on lots of different representations of it, and it gets confusing. We're going to give you the Henry's law constants. It'll be either a table or provided to you. Just look at the units to figure out what the units of the solubility are and what the units of the pressure are. If the Henry's law constant is in atmospheres, the pressure that you're going to get out is going to be in atmospheres. That type of idea. So Henry's law is valid for non-reactive gases, and there is a variant that accounts for reactive gases, but in general, it is considered to be only valid for non-reactive gases and for low concentration entities. So imagine you've got acetone dissolved in water, or water in organic solvents. Okay, water contamination in an organic solvent. Henry's law explains how the water in the organic solvent is going to behave. Conveniently, we don't have a mathematical example this year, but there is a conceptual example. Which of the following are examples of Henry's law? So, carbonation of soda pop, divers getting the bends during diving. The bends is a condition where just nitrogen dissolves in the blood and then all of a sudden spontaneously comes out. Not great. Or oxidation of the blood in the lungs. So which one of those are examples of Henry's law? Carbonation of pop, divers getting the bends, oxidation of blood. Some are, some aren't. Which ones? Well, you can tell me. First one, yes, no, etc. Soda pop is or is not an example of Henry's law? Is an example. Does carbon dioxide react further with water? Anyone? Does carbon dioxide react further with water? It does. So in the context of Henry's law, carbonation of soda pop is not an example of Henry's law. Once again, this despite the textbook saying that it is, it's not based on its own definition, an example of Henry's law. How about divers getting the bends during diving because of nitrogen dissolving in the blood? Is that an example of Henry's law? Does nitrogen react with anything in the blood? Yes or no? Yes, it is. And you're correct. Nitrogen just dissolves in blood. It doesn't react with anything. So that is a true example of Henry's law. How about oxygenation of the blood in the lungs? So oxygenation of blood, is that an example of Henry's law, or does oxygen react with the blood? Anyone? Does oxygen, when oxygenating blood, is that a chemical reaction or does it just dissolve? It reacts with the iron, exactly. So carbonation of soda pop is not an example because carbon dioxide reacts with water. Oxygenation of blood is not an example because in order to bind the oxygen, it binds to the iron in the heme ring in the hemoglobin. So that's not an example. But divers getting the bends during diving, that is an example. I should point out that oxygen dissolving in lakes or river water, that's Henry's law because it just dissolves in the water and of course can be extracted by the fish. But when there's blood in there and it reacts with heme, it's not an example. Good job. Raoult's law. Raoult's law states that the partial pressure of a volatile solvent is proportional to the vapor pressure of the pure solvent. And the proportionality constant is the mole fraction. So here, P of A is the partial pressure of A in solution. P of A star is the vapor pressure of pure A. And chi, that funny looking X is Greek letter chi. Chi A is the mole fraction of A. If you have several or multiple volatile entities in solution, the total pressure is simply the summation of each partial pressure separately. So, for example, ethanol and water, you have the partial pressure of ethanol, partial pressure of water. If there's other things in there, it just gets added on. Should mention that the textbook goes into a discussion on chemical potential and entropy. We're not going into that discussion. We're actually going to discuss entropy when we do chapter 13 and retroactively apply it to this, but we're not going to discuss it here and now. And we're not going to discuss chemical potential at all. So assuming an ideal solution, this is what a Raoults Law Plot would give you. So pure A, and A is red, is the lower volatile species. And so on the bottom left-hand corner, you have a solution that only has A in it. It is the mole fraction of B along the bottom. So pure A is bottom left-hand corner. It has a given vapor pressure. And as the mole fraction goes down, the vapor pressure of A goes down linearly as a result. B is blue. And on the bottom left-hand corner, there is no B. It's pure A. And then you have a little bit of B that is dissolved in A and whatever. And so B goes up to the point where you get pure B on the top right-hand corner. The total vapor pressure is just simply adding together the vapor pressures of A and B. That is what one would assume for what would get for an ideal solution. However, we run into a few problems. First, Henry's law applies to solutes. Raoult's law applies to solvents. So even though this figure goes down in the bottom left-hand corner, down here, B is actually the solute. There's a tiny amount of B present there. We're saying that Raoult's law applies, and actually it doesn't apply. But that's what one would get if it was a pure solvent. Non-ideal solutions show deviations from these laws. And the best example is to look at simply B in that previous picture. What does B actually do? So up in the top right-hand corner, this would be up here, we see application of Raoult's law. It follows what one would expect from about 95 or 85% upwards to 100 to pure B, 85% mole fraction to pure B. You get reasonable following of Raoult's law. Then there's a significant deviation, and down here in the lower 10-15%, you see reasonable application of Henry's law. Henry's law constant is just something you look up, and this is what the solute B does in solvent A. It gets a Henry's law relationship, and that's the slope of that line. Between the two, you see that it kind of does whatever and goes from one to the other, from Henry's law being applicable to Raoult's law being applicable. That's what you actually see for even an ideal solution. Excuse me. It would be ideal if the Henry's law constant was the slope of the pure B vapor pressure, but it's not. And if you want to know why, let's talk activities, honestly. In this example, we have vapor pressure of ethanol and in a water solution. And what you see is that there's deviations. Water is always above the dashed line. The dashed line is what would be predicted by Raoult's law. And over on the far right-hand corner, I'm just going to draw on a line, that would be the Henry's law constant for water. Ethanol does weird things all the way along in the sense that it doesn't stay above or below the Raoult's law. And over here, ethanol is the solute, and it would have a Henry's law constant, actually more like that, and goes from there. So it doesn't even obey Raoult's law up in this corner here. So deviations from Raoult's law. It's reasonably close. It kind of gets close to the values, but it's not exact. I do want to finish this example in class because there's something really important that I need to say after it. So we are going to go through and do this example in class, and I would appreciate if you could hang on for the comments after this. And I need your input on something on that too. So I am going to go through and do this example. So we have mole fraction of B, which would mean that the mole fraction of A would be 0.40 because the mole fraction of B is 0.60. These things, of course, add up to 1. So given the mole fraction of A, the partial pressure of A would be 0.40 times pure A of 23.6 millimeters of mercury, and that gives you 9.44. The partial pressure of B would be 0.60 times 59. Add that all up and you get 35.4. The total pressure is these things added together, and that's 44.8 millimeters of mercury. And of course, this is in the solution. In the vapor, okay, we are going to take the vapor data down here and now calculate the partial pressure of A and the partial pressure of B. For A, it is 9.44, which, I want to point out, we already kind of just mentioned this before, while it is mole fraction, we already looked at mole fraction in relation to volume, and so volume ratio and mole ratio are the same thing. So I can work with, volume ratio and pressure ratio are the same. Let me try that again. pressure ratio and mole ratio are the same thing. We looked at that earlier. Pressure ratio and mole ratio are the same thing. So I can just take the ratio of the pressures here, and for here it's 35.4. And you get 21.0% and 79.0%. Those are the mole fractions in the vapor phase. And they are different than what we started with. If we compare solution phase and vapor phase, the mole fraction of A has gone down and the mole fraction of B has gone up. This isn't the important part. The important part is a question, is an observation I want to make to you. So just want to finish off this bit by saying that the vapor phase always has a higher mole fraction of the more volatile entity than the liquid phase. The vapor phase always has a higher mole fraction of the more volatile entity than the liquid phase. The question I have for you, and I appreciate you staying around, is in regards to today's class, was the presentation of material too fast, reasonably paced, or too slow? And if you wouldn't mind just typing that into the chat. Too fast, reasonably paced, or too slow? Good pace, a bit fast. Most people are saying reasonable. Okay, most people are saying that it was presented at a reasonable pace, a little bit fast by a few people. Definitely not too slow. Okay, the reason why I presented it at this rate and why I wanted to get to this slide is because you have presentations that are coming up associated with your course project. I presented today's slides at a pace of 2.5 minutes per slide. And a lot of you have presented that you're going to do so many slides in your presentation, and like it was 1 minute per slide and the like. Highly recommend you realize that I was doing 2.5 minutes per slide. Some slides I went over really quickly, some slides I spent a little bit more time on, but it was on average 2.5 minutes per slide. And so you, when you're preparing your presentation, when you have 15 minutes, should really have no more than 8 or 9 slides. The title slide really doesn't count. The references slide really doesn't count. But content slides should be no more than 8 content slides in your presentation. That's the information I wanted to convey to you. Through example, I was doing 2.5 minutes per slide. Take that under advisement as you prepare your presentation. Thank you very much, everybody. We will finish off this chapter on Wednesday. Talk to you soon. If you do have any questions, please post them to the chat. I'll be here for a bit.